Hey, welcome back. All right, Module 3. I'm sensing a bit of a vibe as I go through these things. I think your prototypical week will end up being composed of 6 videos of about 15 to 20 minutes each. That's how it's starting to feel, maybe with a short one thrown in every week. I think the last one in this series might be a little short. Well, we'll see. Okay, so this one, the 5th for this week, focuses mostly on Chapter 4. We're in the middle of Chapter 4 now, and I've entitled it Helmholtz, Color and Phrenology. We're going to really start with Helmholtz. Yeah, see, I should be signaling ahead of time. What I've learned from Herbart. There we go. We're going to be starting with Helmholtz, talk about some of the things he did, but I'll focus on his theories of color perception, and then we're going to follow that along by talking about Hering and Lad Franklin and how they've kind of taken Helmholtz's original ideas and updated it a little bit. And then right at the very end, we're going to talk a bit about phrenology, which is always a fun topic. And so, yeah, we will get there. So let's jump right in with Hermann von Helmholtz. Sorry about the upside down name. I don't know, trying to get creative, I guess, and going too far. Okay, here's what I like to start with Hermann. So first of all, everybody who talks about Hermann von Helmholtz begins by talking about what a sort of general scholar he was. He literally taught medicine, physiology, anatomy, physics, and often would be talking about how these things relate to things like the arts. So he was really a man of his world, a deep intellectual, highly respected. He was trained by a guy named Mueller that we're not going to talk about a lot in this course, but he was also a relatively famous guy. And so, a real intellectual's intellectual, let's say. But I think this next thing, which is a quote from Hermann von Helmholtz, is both as revealing as it is almost scary, maybe. But let me just read this. So this was his notion of science. But we cannot triumph over the machinery of matter by ignoring it. We can triumph over it. Yes, this is like a battle with nature, right? We can triumph over it only by subordinating it to the aims of our moral intelligence. We must familiarize ourselves with its levers and pulleys, fatal though it may be to poetic contemplation, in order to be able to govern them after our own will, and therein lies the complete justification of physical investigation. I see the typo there. And its vast importance for the advance of human civilization. So, what he's really saying is science is all about learning the machinery of nature so that we can manipulate it to our own ends. Control. Some would say this is a very male approach to science or to thinking about science, but in fact, many scientists would accept, maybe they'd find this a little hardly worded, but the basic idea that we're trying to understand nature so that we can exert control. Literally, imagine we understood the weather totally so well we could in fact shape the weather, bringing rain where rain was needed and sun where sun was needed. Imagine a world like that. That's what some people think. Now imagine that in terms of psychology. Imagine understanding humans so well, all their levers and pulleys, everything that makes them tick, so well that you could in fact control them, maybe even on a mass level. Is this a good thing? We as psychologists, as students of psychology, is that really, do we hope we're successful? Is that where we hope we get to? At the very least, it's a good point to reflect on every now and then and to think about, why are we doing this and what's the point? And one of the things I'll highlight sometimes in the animal research context is, do we have to make every discovery so darn quick? Are we in a rush to understand nature? Couldn't we just chill a little bit and accept the current conditions as they are and, move ahead, but move ahead with less vigor and intensity? A fascinating issue, a good one just to think about. That's all I throw it out there for. It's such a polarizing quote to say it that way. Now, Hermann von Helmholtz itself is known for a number of contributions to psychology. The one we're going to talk about quite a bit is trichromatic theory. but as well unconscious inference, finger thing, you'll know what that is when I get to it, and wiring. It's all about the endpoints. I'm going to really focus on the trichromatic theory, so let me start a little bit with the finger thing and the wiring, and just to let you know. So the wiring, let's go backwards to forwards. Wiring was really a takeoff of his work with Mueller. And, when we're thinking about the human body as a machine, well, these guys were really your first sensory neuroscientists. They were trying to understand how this machine got input from the world, right, from our senses. And nobody really understood the machine at all. Nobody knew it very well. And what they were famous for arguing is that the nerves that send signals throughout our system, they claim is very much like wires, and critically, they say there aren't sort of separate kinds of nerves for vision and different kinds of nerves for audition and different kinds of nerves for tactile stimulation. They said, no, nerves are all the same. They're like wires in a robot. A wire is a wire. It's not about the wire. It's about the parts that it connects. What part of the body to what part of the brain. And the idea is, the signal itself is just stimulation. It's just stimulation. And so if I, scratch my hand here, well, there's sensory neurons here. And because that sensation of touch originated there, it'll travel all the way up my arm, up through my shoulder, into my brain, and it'll reach, right, the sensory strip on the left side of my brain. You guys should be all cool with this now. But the point is, and it feels like a little scratch. That's what it feels like to me. But the point is, anything that stimulated that part of the brain would feel like a little scratch to me. Even if we could somehow take the wire that starts here normally and make it start over here, let's say, then if that scratched, it would feel to me like this part of my arm is itchy. That's why we can get phantom limb pains, right? The person can have no arm at all, but if that part of the brain is stimulated, it feels like this arm that isn't there is itchy. And so they were very famous on that. And just to kind of follow their analogy that they talk about in the textbook, they say, if pressure here feels one way, it feels like something's touching your arm, right? But if you instead put pressure on your eyeball, it doesn't, it feels the same on the eyelid, but as far as what the eyeball itself produces, we're seeing sort of flashes of light. Be gentle if you do this. But you see little flashes of light. And that's because we're stimulating the retina. And the retina goes to our visual center. And so if that gets stimulated, we get visual stimulation. Okay, so he was big on that work of trying to understand the machinery. He was also big on sensory perception, on thinking about this distinction between what we're aware of and what we're not aware of. And he thought there was a lot of processing that was important that we weren't aware of, that we didn't even notice. And so let me make you aware of something you're not usually aware of. And we did this in Intro Psych, so if it seems familiar, you might remember it. But he would say, let me try to go sideways here. Okay, if you take your fingers and line them up in front of you like this, and now you focus right there on the knuckle of that first finger, and that's where you focus your attention. And now move that second hand away from you, and then move it close. What do you see in that second hand? What you should see now, because I'm allowing you to see it, I'm sort of forcing you to see it, is two fingers back here, like one in the front, of course. Of course you see two fingers, but you see three fingers actually. You see the one in the front, but in the back, you see two. And the further it gets away from you, the further those two fingers go apart. And as it comes closer to that focal point, then the two come closer together again. Okay, so what Helmholtz says is, this is true all the time. This demonstration lets us kind of see it and focus on it because we have the contrast and everything just right. But when we're looking out in the world and we're looking at a person or something in the world, everything else in the world, everything that's not at that point of focus, is in fact producing two images of itself on our retina. Each retina gets a slightly different image. And the distance of those two images apart is dependent on how far that thing is from our point of focus. And so when we focus on something, we kind of know where it is, but we're also learning unconsciously where everything around it is relative to it through these double images that we don't even see. Okay, so that's a little complex, but hopefully you get the sense of it. The important point of that I want you to get is his notion that there are a lot of things going on in our brain to sort out stimuli and sort out the world, because he was interested in sensory input, right? That we're not even aware of, that never even reaches our conscious awareness, but is still critical. And so he was big on this distinction, and it's a distinction we continue to believe today. And one you will see, arise throughout the course. Okay, so let's get to the trichromatic theory then. Again, just to try to give the sense that we're still pre-psychology, right? We're still not really official psychologists yet, but to give you the sense that people were starting to study the mind, the brain, and sensory experience in sort of scientific ways. So in some ways, Helmholtz was more of a theoretician. And so here's one of these diagrams he showed about his notion of light. And you know something, at least from intro psych, and if you've taken perception courses, about how the eye actually senses light. You know about red, green, blue cones and the rods that help us see black and white. They didn't know about all that in these days. Okay, and so really, a lot of that, Helmholtz kind of came to that idea, without being able to do the biological work to actually see all these rods and cones. But he believed that the way we could sense color, which is back to a Newtonian issue, right? The way we could actually perceive color in our minds, even though color wasn't, really in the signal. The light signal is just a frequency of light. But we see color, he said, because he thought we had these three different kinds of receptors, red, green, and blue. So you see each one here is centered around sort of a different color. So this one's more in the, that's kind of a weird one. So he says A is blue. I guess it's more on the blue side of the spectrum, blue, green. Yeah, and B is more greenish, more centered around green, and C is more centered around red. But his important thing is, we often tell you things like there are cones that, fire when green light hits them, and different ones when red light hits them, and different ones when blue light hits them. But what he emphasizes, well, that's what they fire to the most. That's what they're most sensitive to. But outside of that frequency range, they're also sensitive to ones that are close, but their sensitivity falls off. And so if you imagine something in the middle, let's say some point like this, which is a sort of greeny yellow, he would say that's a mixture of, well, not much of this blue, but a good amount of this green, quite a bit of this green, and some of this yellow as well. And these you get a mixture of responses from these things, which allows us to see all of this wide range of color we've seen. So he says, if three basic receptors, we could see a lot of the color in the world. Really impressive, simply because, again, he's nailed it, right? Ultimately, when we got to the point of photoreceptors and how they work, that's what we see, these three different cones that are sensitive to different information. Now, just to kind of show you how, let's look at time a little bit here. Hermann, late 1800s, and now we're going to kind of go a little bit, and we're going to see steps forward in time as we go here. And so I just want to show you how this idea kind of got followed up on and follow the textbook in doing so. So past Helmholtz, there was this guy named Ewald Hering who kind of took on the mantle, or took on the problem that Helmholtz was dealing with. And he said, well, yeah, but we can also see black and white. And he felt that yellow was kind of important. And so Helmholtz said, well, yeah, you can get yellows other ways. But he started to create what he thought were opposites in the color world. So remember that, sort of notion of finding opposites. That was back to Galen, wasn't it? Or back to oh God, I can see his face. My goodness, Socrates student. Yeah, Plato, the idea of opposites. And so he's really kind of created a world, but he's talked about color opposites, where he thinks of red is opposite to green, and yellow is opposite to blue, and white is opposite to black. And so he's created a 3D space where gray is like an equal mix of everything. It's right in the middle. But as you move towards these, you can get, a whiter yellow or a darker or a blacker yellow, if it makes sense. And so he thought this was the real color space. So he's really bringing in rods into the story, right? But he's also highlighting yellow, which we kind of know there aren't yellow cones, but we do also now know that, very much following what Ewald said, that we have these opponent process neurons where, if you remember this from intro psych, so let's take the red-green. That's red or green is coded by a single neuron that usually has a middle firing rate. So it kind of fires like this when neither red or green are present. But if red is present, it speeds up. If green is present, it slows down. And so this one neuron, by having a middle firing rate, can now signal two different things. It can speed up for red and slow down from green. And that's what we know these opponent process nerve cells do. And so he kind of nailed it, that yes, there's only 3 cones, but they feed to the next layer. And the next layer has opponent process ones. And the weird thing is, if both red and green are present, that's when the yellow signal gets in the opponent process. If both red and green are present, it slows down and signals yellow, because yellow stimulates both the red and green cones. Complex. I don't want to bring you through all of visual perception, but I do want you to have that sense that, Helmholtz was pretty darn good for late 1800s. Ewald has kind of taken it a step, and he's not completely accurate, but again, for the point in time they're at, they are doing a really good job of nailing down what the process of transforming light into color in our mind, how that works. And doing so with very little data and a whole lot of thought, which is kind of interesting. Sometimes it's impressive how far you can go with a sort of theoretical perspective informed by data. And we just want to take this story one more step. Christine Ladd Franklin, again, we're a little later in time now, so she knew of the previous work and she was building on it. So in the textbook, you will hear a story, you'll hear quite a bit about any of these female psychologists, these early ones. And it's a story of just how they triumphed against a world that didn't think women should be doing things like this. A world that thought women belonged in the household as good housewives, and that was basically it. She came from a women's right family, so a powerful family that had pushed for women's rights a long time, which partly explains probably her vigor, I guess. And apparently her husband was also very supportive of all of her intellectual efforts. If he had not been, that would have been a problem. So she was able to kind of persevere and have a powerful influence despite it being a real challenge of the times. So very cool in that way. On the color perception thing, she kind of added to it as well by bringing in an evolutionary story. So she's a good example of how Darwin's sort of position has started to sneak into psychology and the way we theorize. And so what she said is she largely bought into where Hering was, but she added an evolutionary layers to it, really, where she wanted to say that the most primitive part of our visual system is all about discriminating white from black, light from dark. The rods, the visual system we need for night vision, that was the most primitive. And that after that, we evolved the ability to see the distinction between blue and yellow. And then only after that did we evolve the ability to see the distinction between green and red. And part of the evidence for this is when we see issues of color blindness, we often see the red and green is the most common form of color blindness that people have. And this is an example of one of the things we'll see in psychology, sometimes called last in, first out, which is the thing that has evolved most recently is often the thing that we see most impacted by any sort of problem, so the most fragile. So for example, conscious memory disappears well before unconscious memory does. Conscious memory is considered to be evolutionarily newer. And so that's just a concept. In the textbook, they actually call this the law of progressions and pathologies. I hadn't heard that before the textbook, but that's what they call this. So this is a concept in psychology, and people were starting to think of the brain that way. Not thinking of it as like it had been created all at once, but rather starting to think that certain parts of the brain are more primitive, and then newer parts of the brain evolved over top of those. And of course, the newest part would be the cortex, and especially for us, the frontal cortex, in evolutionary terms. And so people started to think of that, think of the brain as an evolving system that has vestiges of the past kind of buried within it. Very cool. She was part of that. Okay, good. All right, so that's kind of taken us through Helmholtz, some of the things he did, including the color perception stuff, and then we've talked about Hering and how Lad Franklin have kind of added to that. We're going to take a little bit of a turn now, and just end this lecture with one of the sort of always fun parts of the history of psychology. I don't know why we consider it fun, but this time in which phrenology kind of reigned. And it is an important time because, part of the story I've been telling you is since René Descartes, René said, we are machines. Our bodies are machines. Yes, we have a soul controlling us. We humans do. Animals don't, just humans do. But even humans are mostly biological machine. And so people became very interested in this biological machine. Again, think of Mary Shelley's Frankenstein as an example of that general interest people had in how the human body works. And so part of that started to be this notion of localization. When we think of the brain, remember the evolutionary stuff I was just talking about. When we think of the brain, can we start to think of it as compartmentalized, where very specific parts of the brain are responsible for very specific parts of us and our behavior? That concept is known as localization. And it was really hot. People started to think, is the brain a machine? Okay, the body's a machine. We get that. And then there's this soul or mind thing, and we kind of think the brain does the mind thing. So does that mean the brain's not a machine, or is the brain a machine? And so this was really kind of a lot of interest, and demonstrations of localization were very powerful for making people think the brain is machine-like as well. So I'm going to give you two examples of that, one that has not withstood the test of time and one that has. So the one that has not withstood the test of time is phrenology. Now, the concept of phrenology is kind of cool. And we see it reflected in other biological systems. So you can see why people believe this. The concept is just like this. Think of a muscle. A bicep. If you want a bigger bicep, what do? Well, you go to the gym and you do curls and you do other things that involve using that muscle. And if you exercise it on a regular basis, it will get larger and larger and larger. So the size of your muscle will reflect how much you've worked that muscle. The people who believed in phrenology, Gall and Spurzheim were the big original pushers of this, thought the brain worked the same way. They said, yes, there's a bunch of little modules in there that are devoted to different things. So for example, I don't know, here's one devoted to caution. Okay, they say this part of your brain is the part of your brain that worries about, potential dangers and et cetera. And if you do that a lot, if you're always worried about your safety and always thinking about your safety, well, you're going to work out that muscle quite a bit. And it's going to get big and strong. And you know what that's going to do? It's going to cause a bump on your head. It's going to actually push your skull out. If instead you think more, I'm trying to see what all these words are, and they're tiny. Conscience. Here's your conscience. Okay. So if you have a very big conscience, every time you do something wrong, you feel horrible and guilty and all this stuff, then you should have a bump here. If you're very hopeful, you should have a bump here. Yeah. Okay. And so, that idea, they would actually read your skull and try to look at the bumps that you had. This is just a funny Trump one. I just put this up for you guys if you want. But let me just say that Paul Broca, that idea of phrenology doesn't hold up. Parts of your brain do not get bigger. However, Paul Broca now took this in a different direction. So he noticed that a bunch of patients would all show this problem with speech. And so he followed these patients, literally waited for them to die, opened their brain, and he found that every one of them had an issue at this part of the brain right there, which we now call Broca's area. And so by demonstrating that, he was showing that a specific part of the brain was responsible for a very specific behavior. And this really kind of fed this notion of localization. Okay, so we're going to take that further in subsequent lectures, but I'm going to stop here for now. Thank you. Bye-bye.